Tonight, while you sleep, your brain will shrink most of its connections by about 18%. It is not damage, it is maintenance. Almost everything you learn today will be quietly deleted before morning. What survives is not what you tried hardest to remember. For 4 years, researchers in Wisconsin sliced sleeping mouse brains into ultra-thin sheets and photographed every layer with an electron microscope. They reconstructed nearly 7,000 synapses by hand. The team never knew which brains came from rested mice and which from waking ones. Then they broke the code. A few hours of sleep had shrunk the contact area between neurons by 18%. On average, a synapse is where one neuron touches another. Bigger contact means a stronger signal. Shrinking one means weakening the memory it carries. So the sleeping brain was not resting. It was systematically taking apart the connections it had spent all day building. And it was not sloppy about it. The shrinking hit roughly 80% of synapses. The very largest ones were left untouched. Something in the dark was choosing. Some connections were marked for deletion, and a protected few were marked to survive the night. Which raises the only question that matters here. How does a sleeping brain decide which memories are worth keeping? To understand the deleting, you have to understand what your brain does to itself every hour that you are awake. Learning is physical. When two neurons fire together often enough, the connection between them grows larger and passes signals more easily. That happens constantly. A face, a phone number, the smell of a room, the route you drove home. Each nudges synapses wider. Chiarelli noticed the problem this creates. Almost everything strengthens, almost nothing weakens. The brain only inflates. Bigger synapses burn more energy. They demand more proteins, more supplies, more room. And a synapse near its maximum cannot grow any further. Saturate them all, and learning stops. A brain that only strengthens eventually becomes a brain that can no longer change. Their answer is called the synaptic homeostasis hypothesis. Sleep, they argue, is the price the brain pays for plasticity. During deep, slow-wave sleep, the brain runs the whole thing backwards. It weakens, it shrinks, it renormalizes what the day inflated. Not to erase you, to make room. The morning brain is not emptier than the evening brain. It is emptier in the right places. There is a reason this only works when you are unconscious. The brain cannot learn from the world and rebalance itself simultaneously. Disconnected from the environment, circuits can be replayed offline, tested against each other, and pruned without new input contaminating the result. But downscaling is only half of the night shift. While synapses shrink, something else begins moving through the tissue between them. In 2012, a laboratory led by Mike and Nodegard in Rochester found a plumbing network that nobody knew the brain had. Cerebroside runs in channels alongside blood vessels, washes through brain tissue, and carries metabolic waste out. The following year, they watched it work inside living mice in real time using a technique called two-photon micrography. The result was almost absurd. When the mice fell asleep, the space between their brain cells expanded by about 60%. More space means less resistance. Fluid that barely trickles through a waking brain suddenly floods every corner of the sleeping one. Compared to sleep, tracer entering the awake brain dropped by roughly 95%. Wakefulness did not slow the cleaning, it shut it off. Among the things carried away is amyloid beta, the protein that accumulates into plaques in the brains of people with Alzheimer's disease. Nodegard has a comparison for it. You can host the party or you can clean the house. You cannot really do both. The brain has a limited energy budget. awake and aware, or asleep and cleaning. It appears forced to pick one. So the same slow waves that shrink your synapses also drive the fluid pulses that wash the tissue those synapses sit in. Both jobs load into the same window. Deep sleep is front-loaded, crowded into the first cycles of the night, not the last. So a short night does not shave sleep evenly. It cuts the deep hours first, and a third process is locked to them. This July, researchers described the circuitry connecting deep sleep to the release of growth hormone and found the relationship runs in both directions. Deep sleep triggers the hormone in turn feeds back and helps regulate deep sleep. Each one sustains the other. That feedback loop is part of why the same hours that clear your brain also build muscle and burn fat. Sleep is not one function wearing three hats. It is three systems that evolved to run in the same protected window. Which explains why sleep is universal. Every species studied carefully does it, from fruit flies to humans, at enormous risk. An animal asleep is effectively blind, deaf to approaching danger, and motionless. Evolution does not tolerate a cost like that for nothing. So the forgetting is not a flaw in the design. The forgetting appears to be much of what the design is for. Now return to the synapses that survived. 80% shrank, the largest were spared. That sparing is the entire trick. Picture the day's learning as a field of grass that grew all afternoon. Sleep does not mow it flat. Sleep lowers everything proportionally. Lower everything by the same fraction, and the tallest blades still stand above the rest. The weak signals sink below threshold and vanish. What made a synapse tall? Being used repeatedly in patterns that mattered. Repetition is the vote a memory casts for its own survival. The brain is not choosing your memories at night. It set the rules during the day, and sleep only applies them. That is the elegant version of it. The actual evidence is messier than that, and the researchers involved say so themselves. The 7,000 synapses were mouse synapses in two regions of cortex in adolescent animals, not human brains, not the whole brain. A second team at Johns Hopkins found their own evidence of nightly weakening driven by a protein called HOMA1A. But the two groups disagree about which synapses get downscaled. One says mostly the small ones, the other says mostly the large. The synaptic homeostasis hypothesis remains exactly that, a hypothesis, powerful, well-supported, and still argued over in journals every year. Lymphatic work carries the same caution. Most of it is rodent work. Measuring fluid flow in a living human skull is hard. This matters more than it sounds. The gap between a beautiful mechanism and a proven one is where most science actually lives. What is not in dispute is the outcome. Deprive a brain of sleep and memory, mood and performance degrade, quickly and reliably. Raises amyloid beta in brain regions associated with Alzheimer's disease. Chronic short sleep tracks with higher risk. Whatever the mechanism turns out to be, the brain will not skip the appointment. It only misses it when you make it. So nothing is lost tonight that your day did not already mark as expendable. Sleep is the audit, not the accident. You wake up with less than you had, fewer connections, weaker on average, a brain measurably quieter than the one you fell asleep with. And that is the only condition under which tomorrow can teach you anything at all. Forgetting is not the opposite of memory. It is the price of it. Next time, why the brain that deletes your day spends the rest of the night inventing another.